Hi, in this video, we're going to be solving a problem where we will be finding pipe flow through each, or liquid flow through each segment of pipes and the net flow through each node in a 5-node, 6-pipe system that I have drawn here. So in the video, we'll be using Google Colaboratory to find the flow rates that go through each of these pipes and nodes of water in this system. We can see that we have some knowns here already. We have the pressure of the source node, which is P0 at 200,000 pascals, and that's a set pressure. And then at the sink node, which is node 4, we have a set pressure of 0. We can also see that there all of the elevations or positions of the nodes in the system are at 0 meters, except for the source, which is at 30 meters. And the relative roughness for the entire system is 0.001, and the diameter of all of the pipes in the system are 0.1 meters. So to solve this problem and find what we're looking for, we need to use Bernoulli's equation, which I have written here. And we will basically rearrange it as I have shown, so that we can use pressure, density, or elevation, K value, the fanning friction factor, the length of the pipes, the diameters of the pipes, the velocity of the water, and acceleration due to gravity to solve this problem. And then also on the right-hand side, I have an array shown of all of the pipes in the system. And on the leftmost values in this array are the from node values, so 0 through 3, and all of the values second to that are the 2 nodes, then the lengths of the pipes, and then the K values. So for example, the first section of the array, or the first row, is the pipe going from node 0 to node 1. The length of that pipe is 1.5 meters, and the K value of that pipe is also 1.5 meters. The last thing that I want to show here is this Churchill's equation, and this is going to allow us to solve for the fanning friction factor, which is one of our unknowns in Bernoulli's equation, using the Reynolds number. And it is consisting of these two equations, A and B. So let's go ahead and get started. The first thing that I already have input into Colaboratory is this these two imports, which is NumPy and SciPy, the Newton and root function coming from SciPy, and these will just allow us to use equations like such as square roots and things like that, and pi. That's what NumPy will allow us to do, but then SciPy, the Newton and root function, will allow us to find roots of different equations and to use Newton's method to find the zeros or the roots of equations. In the second cell, I have values for acceleration due to gravity, the density of water, which is labeled as rho, the viscosity of water, which is labeled as mu, the relative roughness for the entire system, since that's a constant among all the pipes, which is ED, and then the diameter of all the pipes, since that's also constant in the system, which is 0.1 meters. So the first thing that we want to do is we want to use Churchill's equation to find the fanning friction factor, since that's an initial unknown that we can solve for to use Bernoulli's equation. So let me pull this back up. So we can use this Churchill's equation, and I'm gonna like put it on the side here, and then put this one. Let's see if I can do that. I can't, so I'll just have to switch back and forth. So we can do this by writing a function, and we'll just call it Churchill. And it's going to be a function with arguments Reynolds number and relative roughness. Obviously, we already know the relative roughness, and we will be able to solve for Reynolds number. So we'll call Reynolds number RE and ED. And then again, Churchill's equation consists of these two functions A and B. And so we'll have to have those within the function, and then we'll return this function for the fanning friction factor. So we just need to type these two in. So U is equal to have to do a little bit back and forth. Apologize for that. I'm going to try one more time to get this to do that, but I don't think it will work. No. Okay, let's. Try to memorize this, punch it in. And then we need B. B is a lot simpler, so I should be able to write it in really quickly. And I also want to note that for this drawing that I have here of these equations, I have B as 37,530 over Reynolds number to the 16th, and that 16 power is incorrect. That's just, I just messed that up. So B is just 37,530 over Reynolds number. That's it. Not to the 16th. Whoops. So, oh, now this is going. Okay, so not to the 16th. And then we just want to return this expression for the fanning friction factor. At 12. Okay. And that should be good. We can test this function with random values to see if it works. We just need a random value for Reynolds number, and we already have our relative roughness. Okay. So now that we have the fanning friction factor, we can go back to Bernoulli's equation and we can focus on the change in head. So let's go back to that. And I just want to say that the left-hand side of this equation, so the difference in pressure over density times gravity, plus the difference in elevation, that side outside of these brackets is equal to the change in head. So if we rearrange this equation and put everything that's in brackets on the right-hand side of the equal sign, then we can write a function for the change in head since we don't know some of the pressures and whatnot. So let's go ahead and start that. It's going to be a function of, let's pull it back up. So it's going to be a function of K value, the fanning friction factor, length, diameter, and velocity. So, or I guess flow rate. Really. So we'll call it D head for change in head. And again, it'll be a function of flow rate, length of the pipe, K value, diameter, and relative roughness. And we don't know, the reason why I went back on my word about saying that velocity is an argument is because we don't know velocity, but we can find velocity by dividing the flow rate by the cross-sectional area of the pipe. Since that's what velocity is, because cross-sectional area times the velocity is the flow rate. So let's write a function for that within the change in head function. So it'll be Q divided by, and obviously the pipes are cylindrical, so the cross-sectional area is a circle, and the area of the circle is pi r squared. We don't know r, I guess we technically do, but we have a value for diameter, so it's easier for us to use that. So our cross-sectional area is going to be pi times the diameter squared over 4. Put that in parentheses. And then for the rest of the equation, so our Churchill equation is what we use to solve for the fanning friction factor, which is what we just did. And what we want to return is this, the negative of this right-hand side of Bernoulli's equation, since that's equal to the change in head, which is what this is being written for. But to be able to do the fanning friction factor in this, we need to have Reynolds number, which we can do because Reynolds number is rho times V times mu over, or rho VD over mu. So we can just go ahead and do that since we've just written something that solves for velocity. So rho VD mu. And now we can return that left-hand side. So let's pull it up. Okay. So before I do that, also, actually, let's just go ahead and write it. So and then again, we'll just use the Churchill function in replacement of that f. So Churchill RE and then we can test this function now with just some random numbers. And so it gave us a value, which means it at least works, but this value is not really correct because if the flow rate is if the flow rate is positive, then the change in head should be negative. And we can correct this by doing some sign convention in the function. Let's see what it does for negative. Yeah, so it's weird looking. Yeah, let's just go ahead and do that. It gave us positive for negative, which is good. But basically the equation for velocity has to be positive because the RE has to be positive, like it has to be just by principle. So the V has to be positive because it's in the equation for Reynolds number, but we still want the sign of the flow rate, but we can just put that back in the return. So we'll just do like the absolute value of this. And then put in the sign. And we want it to be negative. So really, I should have had a negative sign in the return in the beginning because it's like this equation rearranged, but okay, so now let's try it and hopefully it gives us the right thing. I should have deleted it previously, but it's okay. Okay. And it works. So again, when we have a positive flow rate, we want to get a negative change in head, sorry. And when we have a negative flow rate, we want to get a positive change in head. So let's try that really quickly. And it's good. So it should be the same magnitude, just different sign. So delete that. And then we will move on to the next thing. So now that we have a function for the change in head, we can calculate flow rate and use the change in head as an argument, as well as length, k-value, relative roughness, and diameter. So let's get started on writing a function for that. I'm going to call it flow. And again, we will use change in head, length, and k-value, as well as diameter and relative roughness as arguments. And to do this, we will have to find the roots of Bernoulli's equation. And we can do that using Newton's method, which is kind of what I was talking about at the beginning that you import with SciPy. And it requires us to input a function and an initial guess, and then take those to 0. So we're going to have to write in another, like come up with another function and come up with a initial guess for that function, which we can drive to 0, but that will all be within this flow function. So I'm going to leave it here for now. And then we can write another function that will have what's inside to take it to 0. So I'm going to call it f to 0 since that's its function. And since we're just taking the roots of Bernoulli's equation, it's essentially the same thing as the d-head thing. So we can just copy and paste these in there. And then we want to return Bernoulli's equation. So it'll be delta head plus the left-hand side. So, and if you notice that there needs to be that this delta head is written as a different variable than the other one, which is d head, it's because we want to differentiate between a value and a function. So. I think we can just copy and paste this actually from here. We don't need the signage thing. I don't think. Yeah, I don't think so. So that should be good. And we can test it with random values, I guess. So oh wait, no, we can't. Because we can't test it until it's actually like in there. Just like that. So, okay. So now we have to do the initial guess thing. And we can do this. So what we're doing is we're making an initial guess of flow rate. So we can do this by first making a guess for the fanning friction factor, and then just use that to find velocity, which is that V equation, which then we can use with the cross-sectional area to make a guess for that initial guess for the flow rate. And then with the guess and the equation that we just wrote, the f to 0, 1, it will iterate it using Newton's method to find the zeros, and then those will be the actual flow rates. So we can go ahead and do that. So we'll call it Q guess. And again, that's going to be the cross-sectional area. I should really just be copying and pasting this because it'll make it much faster, but it's okay. Yeah, and then it'll be the velocity. So we'll have to like rearrange Bernoulli's equation for that velocity. So it will just be, since it's velocity squared in there, it'll be the square root of, it'll just be the square root of delta head over K plus 4, and then also we can do a fair guess for the fanning friction factor instead of like writing in the whole Churchill thing, and just say that it's 0.01 because the range for the fanning friction factor is very small, and that's a pretty reasonable guess. So we can just use that since it's just a function for the initial guess anyways. So we make it, oh, why does it look like that? Oh, never mind. 0.01. Unexpected EOF. I don't know what that means. Yeah, another. Where's the ending? This doesn't have an ending. Parentheses. Okay, so that's fine because we're gonna put it in there. So let's put both of these inside of this. Now we can just delete this. I think I have to indent all of these since we want it to function inside. Oh, okay. And then we can just delete this. Okay. Great. So now we can, well, we already put them in there. So I guess now we can just test values. So let's give a random value for delta head, 7. Oh, well, okay, so that's the most important part. We have to, so now the whole point of this, of the flow is that we will find the roots of this equation using that p-guess. So again, we can use Newton's method, which is the SciPy function. So we want, let's copy and paste it. I don't know which is faster. We want resulting flow rate. I think that's in the right spot, to be equal to Newton So it says that it failed to converge after 50 iterations and that the value is super small. Oh, I think it's because we have to add in, there's a few different things that I'm pretty sure we can simplify, and then we also need to add in different parameters so that if the delta head is really small, it won't mess up because it will mess up otherwise. So basically, if the absolute value of delta head is smaller than a really, really small number, so like 1 times 10 to the negative 10, we want it to just return a 0. So I'm going to add that in first, and I'm also going to change all of the delta head variables values in the function to be the absolute value of delta head, and then we'll add that sign back into the return. So we'll just give it a, so we don't have to do it every single time. And let's go ahead and give value to this indent. We're going to do that using numpy, this function by numpy. And then we'll just do an if statement for if the value is super small, we want it to return 0. So if absolute value of delta head is less than 1 times 10 to the negative 10, which is very small, we just want it to return 0. And then let's change all of the delta heads to absolute value of delta heads. I think that's the only one. And then we'll just have to do, or no, this, let's see, as well. And then we want to put the sign back in the return. So okay, and that should be good. And then the last thing, space this out a little bit so it looks clean. The last thing that we're gonna do is simplify the return of the f to 0, because it is basically equivalent to the delta head function minus the delta head value, like the absolute value. So, oops. I think that's all it asks for. Minus the absolute value of delta head. Okay. So, okay. Okay, cool. So that's a good sign. We want a positive value to give us a negative, and we want a negative to give us a positive of the same magnitude. So we're good to go with that. Yeah. So now we can work with this array of pipes like we talked about in the beginning. I already have it typed in here since we don't really need to waste time watching me punch in numbers, but again, the values in order of the row are the from node, to node, the length, and the K value. So now that we have that in, we can go ahead and we can start solving for the entire system. So let's go ahead and also give values for all of the elevations since we already know that. And we'll call that Z. So we'll make an array. And again, all of those elevations are at 0 except for the source node, which is at 30 meters. So easy. One, two, three, four. Okay. And then we also know the pressure for the external nodes, so we can actually go ahead and add that as well. First, let's just go ahead and provide an index for the external nodes. So and they're indexed at 0 and 4 because the first row in the well, we have nodes 0 to 4. Node 0 is the source, node 4 is the sink. So and then we'll give them, we know their pressure, so we can also provide something for that, another array. And the source was at 200,000. And the sink was at 0. And then we can identify what each thing, like what each position in the array, the pipes array represents. So like we can say that we can specify which position is the from node, the to node, so that we can pull those as well easily. I'm gonna space this out so it's a little bit easier to read. So we'll just go in order. So the from node is indexed at 0. So we can just do 0. We want it to be as type integer because it can only be an integer. It's just an integer value. It's just from 0 to 4, at least for this system. So we can specify using this. The same thing for the to node, and that's indexed at 1. Do the same thing for the lengths. That's indexed at 2. And lastly, the K values. And that is indexed at 3. So that is our entire array. And the lengths and the K values are not just integers, they're also decimals, so we don't want to do the as type integer thing. So what else can we specify? We can we can give the number of pipes, which will just be the shape of the array. So like the number of rows. Really, that's not as needed for this problem since there's only 6 pipes. We just, well, I guess that's not true. It is needed. But basically, like a lot of this is provided so that if the system were to get bigger and bigger and bigger, it'd be easy to implement. So we can do the shape. We know the diameter and the relative roughness, and it's the same for all of them, so we can specify that too. We can use NP full since it's the same for all the pipes. And use N pipes, and then it's 0.1 plus the diameter for all of them. Reset. And then the same for the relative roughness. And use NP full since it's the same. And then we can also specify the number of nodes because it'll just be the maximum index plus 1 since the indexing starts at 0. And we can use np.max function for that. And this is also going to be an integer. And then just add 1. And I believe that is all of the information that we want to solve the rest of the problem for the entire array. So now what we want to do is we can write a function to find the flow of the entire network. And to do this, we'll have to write a function that computes all of the flows from the internal pressure because the total internal pressure of all the internal nodes is equal to 0. So we can then use that function to find the net flows at each node by using the root function and adjust the internal pressure values. So we'll have to start writing another function again just to find the net flow with head as an argument. So we can also get rid of this. Just so. And we'll just call it calc flows since that's what we're calculating. And again, we're using heads as an argument. So we'll receive heads and return flows. And first, we'll just assign the flow in each pipe 0. So we can use the numpy zeros function for that using our n pipes value that we already specified. And then we can use a for loop so that we have it for the entire array. So, and we'll use the n pipes again. And net flow is the difference in the head in the from node and the to node. So we can do that to calculate flow. So that's what we're going to do on our for loop, and we'll iterate that for the entire array. So delta head is equal to the heads in the two nodes minus the heads in the from nodes. Okay. And then flows flows is what we want to return. So it'll just be flow using delta head K value is the diameter and the relative roughness, since it's a function of all those. And again, we specified, yeah, we called it length, so we called it K. Again, like we're doing this for the whole array, so that's why we had to write all of these things in. And then it's just simpler to do it. So pipe, the diameter is pipe D. Whoops. And then putting the I in the brackets will let the for loop iterate it for the entire array. Still need relative roughness, which we call pipe underscore ED. I think that's it. And then we want to return flows. So let's test this with just like random values of head. And then we can actually write something that is for the heads for this. So we'll just say, we'll have to give it an array or write it as an array since it's for our whole array of pipes. So we need 5. So 1, 2, 3, 4, 5. And then calc flows of heads. Oh. Okay. I do this in every single video. So I don't know why I continuously do this. I need to change. These are not matching up because my from nodes and to nodes they don't match, like the value or the variable name. So in some of them I wrote from node to node, and another ones I wrote nodes. But I think there's only one place to change it, and it's just this. Okay, yeah, so it worked. That's awesome. And it also makes sense because all the heads that I put in are positive, and it gave back all negative flows, which is good. So delete that. But now let's actually give something for the heads. So we'll initially just make them 0, like we're going to do for everything. for the end nodes, since it's all the nodes. And then we can just rearrange Bernoulli's equation to compute head, since the pressure is known. So zeros and nodes, and then, or at least we can do it for external nodes, I guess, because we know that it's 200,000 and 0. So external. Yeah, that's pressure over rho times G, and we have something for external pressure. I think it's external G, yeah. And then over rho over G, and plus elevation, which would just be Z, but just for 0 and 4 index, because again, it's just the source and the sink node. Right. Yeah. Oh, but we can just do Z external nodes. Yeah. Yeah. Yeah, because we already specified 0 and 4. Okay, cool. So, yeah. So now we can calculate the flow in each pipe. Like we said before, we can calculate the flows we can calculate the net flows by writing a function that will use the pipe flows as an argument. So that's what we just did. And now we're gonna compute or write a function that computes the net flows. So I'm gonna call it calcnetq. Yeah, calcnetq. And it's going to use flows as the argument, which is the return of the function that we just wrote. And it's going to return net q. So so what do we want to put in here? What we want to do is we're going to use the add function. And we're going to basically add the flow in the netq array to the 2 nodes position as positive, and the flow in the array of the from nodes position as negative. So basically, you want to add the flow in the 2 nodes and you want to subtract the flow in the from nodes, because it's like coming and leaving. So the netq, well, we'll first set it equal to 0, like we're going to do with everything, of n nodes. And then netq in the from nodes is going to be positive flows. So np.add at netq in the 2 nodes. So those are the indices. Is flows. And then use the same function and do the indices for this one's the from nodes, and it'll just be negative flows. Okay. So now we need to give the value to the internal nodes, which we can do by just subtracting the external nodes from like the list of nodes. So we just need to like basically identify the internal nodes since we only did that for external nodes. So internal nodes. And we can make it a list. Since we already have, we will just subtract the external nodes from n nodes. So list set range is n nodes, and then minus set external nodes. And then from here, we can set up a function to find the net flow in the internal nodes. And it'll use pressure as an argument. And it'll solve for the head at the internal nodes. So what do we call it? I guess going crazy. That's what we're defining it as. Net Q internal, the net flow. And it's going to take in the internal pressures. And it's going to calculate the heads of the internal nodes. And we'll have to like make guesses because this is another function that we're going to drive to 0. But let's go ahead and write it in first. So internal nodes. And again, it's pressure over rho times G plus elevation. Plus elevation at the internal nodes, which we already actually do know, just 0. Yeah. For all of them, so I don't really know why. And then we'll return it. So we'll return like this function, but using the flows, using the heads. At the internal nodes. Now we can use this. We can use the SciPy root function and this net or the calcnet Q flows function, or no, the net Q internal function. The only thing that we need now is a initial guess for pressure. And we can easily do that. All we have to do is calculate it from a guess of the heads, which we can just average from the external nodes because that's a fair guess. So first we'll do an internal head guess. And again, it's just going to be the average of the ones of the external head guess. And we can use numpy mean to average those, use it as a function. So the heads at the external nodes. And then we can calculate a guess for internal pressure from this, since it's just head plus the elevation. times rho times g. We know the elevation. Or yeah. Let's pull it back up. I kind of forget. So it'll be the head minus the position times rho times g. So minus, because the elevation, the internal, and then multiply that times rho times g. And that's our guess for internal pressure. And now we can use the root function to get our solution. So we'll be able to find the actual pressures of the internal nodes. So we'll just call it result because it's the root using net Q internal and then our internal P guess. So and then Q internal. And then let's just see. Keep doing it. But we want to turn that, so now I'll give it this. Okay, it worked, yay. Okay. We are basically done. We just want to basically print what we have found. So first we'll just give a value for the calculated flows. So it's going to be calc flows of heads. That way we can just write in calculated flows. Calc flows of heads. And then we can use a for loop to basically print everything for the entire array. So for I in range. And then we'll use n pipes since that's all the pipes, because we'll do it for the pipes first. We want to print we'll do so this first one, we're just gonna print the flow in each pipe. So we can print, we'll just have it in like 6 different rows from node to node, from node to, or from node to node flow, from node to node flow, so that we don't really have pipe numbers, we have from nodes and to nodes, but you can see like 0 to 1, this is the flow, 0 to 2, this is the flow. So you can say from integer zero. So that's the from. And then that's the from node. And the to node will be that's the index.1. So I1. The flow, and that'll just be calculated flows with I. So it's 11. Yeah. Good. I didn't finish. Um, er, oh, okay. Then that's good. Yeah, that looks good. Looks great. So 0 to 1, 0 to 2, 1 to 2, 1 to 3, 2 to 4, 3 to 4. We have the flows in each pipe. So now let's do the net flow. And we'll just do the same thing, like calculated net flow at Q. It'll be this. And then we'll have to set the pressure is equal to 0. For all of the nodes, except for, well, not except for, but the pressure of the external nodes we already know. So external nodes, and we already have a value for external T. And then the pressure of the internal nodes is what we just found. It was result at dot X. So pressure internal X. And now that we have everything written out, we can use a for loop to print out. So we'll just, well, I guess we can't really copy and paste. We have to write it. And we'll do node pressure and net flow. And then it'll just be I. Pressure. Do pressure is equal to, or just make it look pretty. There's really no point, but it's fine. So it's showing for each node, so net flow. This is wrong. This needs to be pressure. Yeah. Right. And then this will be the calculated net Q. Okay, so okay. So we're done. So, and it looks good because we can see every node, one or 0 through 4, and we can see that the pressure at node 0 is 200,000, which was just a node from the beginning, and the pressure of the sink node, node 4, is 0, which again we know at the beginning it's a fixed pressure, so it stays the same the whole time. We can see that the net flow in the source node is the magnitude of it is equal to the net flow in the sink node, just with a different sign. And it makes sense that it's negative going through the source node because it's like leaving, and then it's positive going through the sink node because it's coming through. And it also makes sense that the net flow in all of the internal nodes is so close to 0 because, again, like we said previously, the total internal flow should be 0. So thank you for watching this video.